Number 1. Anomalocaris. 500 million years ago, the Cambrian Ocean was a world of tiny, soft-bodied organisms. Most measured just a few centimeters long. They had no jaws, no claws, no meaningful way to fight back. Then, one creature broke every rule of scale. Anomalocaris reached 1 meter in length, about 3.3 feet. Among centimeter-sized fauna, this was the biological equivalent of a blue whale materializing in a tank of goldfish. It was the world's first apex predator. It did not just dominate the Cambrian Ocean. It invented the concept of predation at scale. This happened during the Cambrian explosion, often called biology's Big Bang. Within roughly 20 million years, nearly all major animal phyla appeared. The evolutionary steps leading to Anomalocaris represent the earliest known leap in predatory body size and anatomical complexity. Nothing before it had attempted anything like this. 2 massive compound eyes sat on stalks protruding from its head. Each contained roughly 16,000 individual lenses, making them the most advanced visual system on Earth at that time. To translate that into modern terms, its prey relied on simple eye spots that could barely detect light from shadow. Anomalocaris could resolve shapes, movement, and distance. Researchers have described this sensory gap as that of a god among the blind. In front of its circular mouth, 2 spiked grasping appendages extended forward like impaling arms. These structures seized trilobites and soft-bodied organisms, corralling them toward a ring of sharp, overlapping plates. That mouth functioned like a nutcracker. It could crack trilobite exoskeletons in a coordinated strike. Propulsion came from flexible lateral flaps running along its body, granting it maneuverability and speed unmatched in Cambrian waters. Its body was highly segmented, covered in a chitinous exoskeleton that required periodic molting for growth. It was a solitary hunter. No evidence suggests pack or swarm dynamics. The history of its discovery is one of science's great misidentification stories. Charles Doolittle Walcott first examined its fossils in 1892 and classified the grasping arms as shrimp bodies, the circular mouth as a separate jellyfish, and the main body as yet another organism entirely. For nearly a century, one animal was catalogued as 3. It took Harry Whittington's reanalysis at Cambridge in the 1970s to unify them. Fossils have since been recovered from the Burgess Shale in Canada, Xinjiang in China, and sites across Australia, confirming a global oceanic distribution. The mainstream theory holds that Anomalocaris was a visual pursuit predator actively hunting trilobites. An alternative view favored by some paleontologists argues it was primarily a scavenger or soft prey specialist. Their reasoning is structural. The mouth plates could not fully close, meaning hard-shelled trilobites may not have been its primary food source. Then there are the fringe hypotheses. Its sudden appearance in the fossil record has fueled Cambrian trigger theories, ranging from gamma-ray bursts irradiating Earth's surface to rapid oxygen spikes catalyzing neural complexity. None have gained mainstream acceptance, but they remain subjects of genuine scientific curiosity. Anomalocaris paved the way for all future giant arthropod predators in the Paleozoic. Its 16,000 lens eye design now informs biomimetic research into wide-field cameras and multi-aperture optical systems. But the Cambrian oceans were just the opening act. 200 million years later, the killing moved into the air. Number 2. Meganeura. By the late Carboniferous period, over 300 million years ago, Earth's atmosphere had changed radically. Oxygen levels had surged to approximately 35% compared to today's 21%. That 14% difference changed everything biology could build. The evolutionary steps matter here. Insects breathe through a tracheal system, a network of tubes that delivers oxygen passively from the atmosphere directly to tissues. There is no lung, no active pump. This means the concentration of oxygen in the surrounding air directly determines how large an insect body can grow. At 35% oxygen, the upper size limit expanded dramatically. Meganeura's wingspan reached up to 75 centimeters, roughly 2.5 feet. That is comparable to a modern hawk. It was the largest flying insect that has ever existed. The world it inhabited was Earth's first vast coal forest. Dense, humid swamps filled with towering lycopsid trees and giant ferns produced the very oxygen that fueled insect gigantism. Those forests would eventually become the coal deposits that powered the Industrial Revolution hundreds of millions of years later. Charles Brongniart first described Meganeura's fossils in 1885 from coal deposits near Commentry, France. Its spiny legs were specialized for snatching prey in mid-flight, a biological grasping mechanism perfected millions of years before any raptorial bird evolved. Mandible strength was sufficient to crush almost anything it captured, including other large insects. Estimated flight speeds rivaled modern dragonflies, reaching up to 35 miles per hour. It hunted in swarms rather than as a solitary predator, turning the air above carboniferous forests into coordinated killing zones. It was the primary aerial predator of its era. No vertebrate flyer existed to compete. The mainstream explanation for its size is hyperoxia, directly enabling giant insect body plans through passive tracheal oxygen delivery. An alternative hypothesis suggests gigantism was driven not only by oxygen, but by the absence of aerial vertebrate competitors, an empty ecological niche. A more speculative proposal argues that carboniferous atmospheric pressure was significantly higher than today's, further aiding flight mechanics for massive insects. Modern laboratory experiments confirm that current oxygen levels are physiologically insufficient to support insects of this magnitude. Researchers have reared insects in hyperoxic chambers and observed measurable size increases across just a few generations. A Meganeura bite could shred human skin. Not large enough to consume a person, it could still cause severe lacerations to the face, ears, and neck. Massive wings beating overhead would have been both visually and acoustically overwhelming. Survival in this environment required constant 360-degree skyward vigilance. These coal swamp ecosystems collapsed as the supercontinent Pangaea dried, ending the conditions for such gigantism permanently. Meganeura's flight mechanics, particularly its fore-wing configuration and vein-supported membrane structure, now influence microdrone aerodynamic design. But while the skies were terrifying, the forest floor held something even stranger. Number 3, Arthropleura. Arthropleura armata holds a record that still stands. It is the largest known land invertebrate in the entire fossil record. Specimens stretch between 1 and 2.6 meters, approximately 8.5 feet, with a body width of roughly half a meter. Dozens of heavy, armored, jointed segments moved in rhythmic, rippling waves. It was in effect a millipede the size of a car. The same hyperoxic carboniferous atmosphere that built Meganeura also fueled Arthropleura's terrestrial gigantism. It inhabited the dense coal swamp forests of what is now Europe and North America. Fossil trackways have been found in Scotland and Nova Scotia. In 2021, researchers at the University of Cambridge described a major specimen from Northumberland dated to approximately 326 million years ago. The creature was first described scientifically in 1854. Despite its terrifying appearance, Arthropleura was likely not a predator. The mainstream theory classifies it as a peaceful giant detritivore, essentially a colossal millipede filling the role of nutrient recycler, consuming plants and decaying organic matter. An alternative view points to trackway evidence showing it moving through diverse terrain, suggesting opportunistic omnivory and more active foraging than previously assumed. Its danger was not intentional. Sheer mass could crush a human-sized organism accidentally. Researchers describe this as accidental lethality. It may have secreted irritating chemicals as a defense mechanism, similar to modern millipedes, but potentially far more potent. The fringe speculation centers on these secretions, proposing they functioned essentially as a biological chemical weapon system. Brushing against Arthropleura could trigger chemical exposure affecting the eyes and lungs. Its armor plates glinted in ambient light, forming a living wall across the forest floor. It often sprawled across narrow paths, creating physically impassable obstacles. Primitive weapons would have been ineffective against its heavy, segmented armor. It was slow and methodical, but its size meant it did not need speed. Arthropleura vanished as oxygen levels dropped and carboniferous forests gave way to drier Permian landscapes. No descendant lineage survived. Its segmented, flexible armor now informs modern research into articulated protective gear for military and industrial applications. Its respiratory biology informs research on how atmospheric oxygen constrains maximum invertebrate body size, a question directly relevant to astrobiology and exoplanet habitability models. But while these giants roamed the forests and skies, something far worse was waiting in the water. Number 4. Jaekelopterus. Rhininae is the largest arthropod ever recorded. It exceeded 2.5 meters in total length, over 8 feet. It lived approximately 400 million years ago during the Devonian, often called the Age of Fishes. But this was no fish. It was a eurypterid, a sea scorpion. Its hunting ground was not the open ocean, but freshwater environments, rivers, estuaries, and shallow banks. Its claws, known as chelicerae, measured nearly half a meter long, roughly 18 inches. Biomechanical analysis suggests they were powerful enough to snap bone. The eurypterid lineage dominated aquatic ecosystems for over 200 million years before declining. They breathed through book gills, layered respiratory structures similar to those of horseshoe crabs, their closest living relatives. Its hunting strategy was classic ambush predation. It remained perfectly still in murky water until prey wandered close. Compound eyes capable of spotting tiny movements from several meters away, even in low visibility water, gave it a decisive sensory advantage. Strike speed was explosive. A sudden lunge dragged prey underwater before it could react. Once those claws locked on, escape was virtually impossible. It could grip and crush simultaneously. Standing ankle-deep in Devonian water placed an organism within its engagement zone. It could vanish with captured prey without leaving a surface trace, often mistaken for a submerged log or rock until the moment of attack. The type specimen's chelicera claw was described by Brady, Poschmann, and Tetley in 2007 from the Rheinische Massif, Germany. The mainstream theory positions Jaekelopterus as an apex freshwater predator exploiting the same ecological niche as modern crocodilians. An alternative view suggests it may have been semi-amphibious, occasionally hauling onto riverbanks like modern horseshoe crabs. The fringe question concerns its environment. Its extreme size raises the possibility that Devonian freshwater ecosystems had significantly higher dissolved oxygen or nutrient density than modern equivalents. Eurypterids declined sharply after the Devonian as jawed fish diversified and outcompeted them. No lineage survived past the Permian. Jaekelopterus's chelicera biomechanics now influence robotic gripper design, particularly for underwater manipulation systems. But the Devonian had an even more formidable killer in deeper water. Number 5. Dunkleosteus. Dunkleosteus terrelli lived approximately 360 million years ago. It was the Devonian's armored executioner, and it may have possessed the most powerful bite of any fish in Earth's history. Its head and thorax were covered in thick bony plates, a natural suit of armor, unique among large marine predators. It reached lengths of 6 to 10 meters, roughly 20 to 33 feet, and weighed over 1 metric ton. Instead of true teeth, it possessed 2 pairs of sharp bony plates functioning as self-sharpening shears. The upper and lower plates occluded in a way that honed each other with every bite, like scissor blades. The edges stayed razor keen through constant use. This is the same engineering principle behind modern self-sharpening industrial cutting blades, independently reinvented by human engineers without knowing nature, solved it hundreds of millions of years earlier. Bite force has been estimated at 6,000 to 7,400 newtons. Anderson and Westneat at the Field Museum calculated these figures in 2007 using biomechanical modeling. That places Dunkleosteus among the most powerful bites in the entire history of vertebrate life. It could open its mouth in 1/50th of a second, just 0.02 seconds, creating a suction vacuum that pulled prey inward. The Devonian, the Age of Fishes, saw the first radiation of jawed vertebrates. Dunkleosteus was the apex expression of the Plesioderm lineage. It was cannibalistic. Fossil evidence shows it frequently preyed on its own kind. Bite marks on Dunkleosteus armor and regurgitated bone deposits confirm intraspecific predation. Its crushing jaws allowed it to eat anything in its environment, including other armored placoderms and early sharks. Heavy armor made it a relatively slow, tank-like swimmer. It sacrificed speed for near invulnerability. Well-developed eyes and potentially a lateral line system gave it a multimodal sensory suite. Named for David Dunkel and J. Terrell, its fossils have been found in North America, Europe, and Northern Africa. New specimens discovered in Morocco in 2023 expanded its known geographic range. The mainstream theory describes it as a slow-cruising apex predator dominating shallow coastal waters. An alternative view based on hydrodynamic modeling proposes it was more of an open water pursuit predator than its heavy armor suggests. The fringe speculation is ecological. Its extreme bite force and cannibalism may indicate Dunkleosteus populations were ecologically unstable, locked in arms race feedback loops that could have contributed to placoderm extinction. It went extinct during the late Devonian extinction event, possibly linked to ocean anoxia. Its specialized armor and jaw structure represent an evolutionary dead end with no surviving descendants. But in the seas of a later era, something far more anatomically bizarre was taking shape. Number 6. Helicoprion. Helicoprion lived from the early Permian to the early Triassic, approximately 290 million years ago. Its defining feature is one of the strangest structures ever documented in any animal. A tooth whorl in its lower jaw resembling a circular saw blade. The whorl sat at the symphysis, the midline junction of the lower jaw. New teeth continuously pushed older ones forward into the spiral throughout the animal's lifetime. Unlike most sharks, which shed individual teeth, Helicoprion retained every tooth it ever grew. The whorl accumulated them into an ever-expanding coil. When the mouth closed, the whorl rotated slightly to act as a slicing tool, sawing through soft-bodied prey. Each tooth was serrated along its edges. Estimated total length ranged from 5 to 8 meters, comparable to a modern great white shark. Its cartilaginous skeleton meant that nearly all of its body has been lost to time. Only the mineralized tooth whorls commonly fossilize. This created one of paleontology's longest-running identification puzzles. Alexander Karpinski first described the fossils in 1899. For the next 114 years, scientists debated where the whorl actually sat on the body. Proposals included the nose, the dorsal fin, the tail, and the throat. It was not until 2013 that Leif Tapanila and Jesse Pruitt at Idaho State University used CT scanning to confirm its position in the lower jaw. The Permian Ocean was recovering from the late Devonian extinction, creating ecological vacuums that bizarre specialists like Helicoprion filled. It was a fast pelagic open ocean swimmer with a highly developed sense of smell and electroreception, a sensory suite typical of high-end shark relatives. Tooth whorls have been found worldwide, from Idaho to the Ural Mountains to Western Australia. The mainstream theory identifies Helicoprion as a specialized cephalopod predator, using the whorl as a slicing apparatus against squid and ammonites. An alternative theory proposes the whorl function more as a trap or cage, preventing prey from escaping the mouth during capture. The fringe speculation is that the tooth whorl served a display or sexual selection function rather than a purely predatory one. Helicoprion was one of the very few Paleozoic shark lineages to survive the devastating Permian-Triassic extinction, though it died out shortly after in the early Triassic. Its tooth whorl mechanics are now studied for insights into bio-inspired cutting tool design and continuous dental growth systems. But while Helicoprion patrolled Permian seas, something enormous lurked in Permian freshwater. Number 7. Prionosuchus. Prionosuchus plumeri was the largest amphibian ever discovered. It lived during the Middle Permian, approximately 270 million years ago, in the massive lagoons and river systems of what is now the Parnaíba Basin, northeastern Brazil. Estimated length reached up to 9 meters, about 30 feet. The skull alone measured over 1.6 meters, more than 5 feet. The evolutionary steps here are important. Amphibians had been the dominant freshwater predators for tens of millions of years by this point. True crocodilians would not evolve for roughly another 40 million years. Prionosuchus occupied that niche first. Its body plan closely resembled a modern gharial, long, narrow snout, powerful tail, semi-aquatic posture, with eyes positioned on top of the skull to monitor the surface while nearly fully submerged. Hundreds of small, needle-sharp teeth lined its long snout, designed to grip slippery fish. The snout specialized for rapid side-to-side strikes in water, a technique modern gharials still use for fish capture. As an amphibian, it possessed lungs but likely also absorbed some oxygen through moist, permeable skin. No scales, unlike reptiles. Primarily aquatic, using its powerful tail for propulsion, it was likely clumsy and vulnerable on land. In the water, it was a different story. As an ectotherm, a cold-blooded animal, it could survive long periods without food, but was lethally efficient when metabolically active. Its bite style was snap and hold rather than the death roll of modern crocodilians. The jaw structure did not support rotational force. It likely produced deep, low-frequency bellows or grunts for territorial communication. L. iPrice described the type specimen in 1948 from Permian deposits in Piauí, Brazil. The mainstream theory classifies Prionosuchus as an ecological analog of modern crocodilians, filling the apex freshwater ambush niche long before crocodiles existed. An alternative view argues it was more of a specialized piscivore, a fish eater, based on its narrow snout morphology. The fringe question is environmental. Its extreme size for an amphibian has prompted debate about whether Permian tropical freshwater systems had fundamentally different productivity levels or oxygen concentrations. Prionosuchus disappeared as the Permian climate shifted toward increasing aridity, drying up the swampy habitats it depended on. An environmental specialist doomed by climate change. But on the dry land of that same Permian world, something more familiar looking and far more deceptive was already dominant. Number 8. Dimetrodon. Dimetrodon lived during the early Permian, approximately 295 million years ago. It predated the first dinosaurs by roughly 50 million years, and here is the critical fact most popular depictions get wrong. Dimetrodon was not a dinosaur. It was not even a reptile. It was a synapsid, part of the evolutionary lineage leading directly to mammals. It is more closely related to humans than to any dinosaur that ever lived. It grew over 3.7 meters long, about 12 feet, stood 1 meter tall at the shoulders, and could weigh up to 250 kilograms, roughly 550 pounds. Its defining feature was a massive dorsal sail supported by elongated vertebral spines, adding roughly another meter to its total height profile. The skull was enormous, filled with two distinct types of teeth, a condition called heterodont dentition, shearing teeth in front and crushing teeth in back. This is unlike the uniform teeth of most contemporary reptiles. It represents a critical evolutionary step toward the differentiated dentition seen in modern mammals, including the molars, canines, and incisors in your own mouth. Edward Drinker Cope first described Dimetrodon in 1878 during the Bone Wars era of competitive American paleontology. The mainstream hypothesis for the sail's function, developed by Bramwell and Felgate in 1973, holds it was primarily a thermoregulatory organ. Blood vessels running through the membrane allowed rapid heating when basking and cooling when turned sideways to the wind. This gave Dimetrodon a metabolic advantage, warming up faster than rivals each morning. Think of it as nature's first solar panel. An alternative theory proposes the sail served primarily as a sexual selection display, like a peacock's tail, with thermoregulation secondary. The fringe speculation suggests the sail could change color or pattern via blood flow, functioning as a dynamic visual signal. No fossil evidence confirms or denies this. Its jaw force was capable of crushing bone. Muscular legs positioned partially beneath the body could lift its torso off the ground for surprisingly fast locomotion. It combined speed and ambush tactics, sprinting in short bursts to strike prey. It was the apex predator of the early Permian, dominating everything in its terrestrial ecosystem. The sail's intimidation factor made it appear far larger and more formidable to rivals and prey alike. Dimetrodon's sail thermoregulation hypothesis now directly informs biomimetic research into passive solar heating and cooling systems, the geometry of surface area to volume heat exchange. But later in the Permian, something faster, smarter, and far more lethal was evolving. Number 9. Gorgonopsians. The Gorgonopsians were the apex terrestrial killers of the late Permian, ruling from roughly 260 to 252 million years ago. The largest species, such as Inostrins via, reached 3.5 meters long, about 11.5 feet, and stood chest-high relative to a modern human. Their most conspicuous weapons were saber-like canine teeth, as long as a human hand, approximately 12 to 15 centimeters in the largest specimens. The evolutionary lineage matters. Gorgonopsians were therapsids, mammal-like reptiles, part of the same synapsid lineage as Dimetrodon, and ultimately modern mammals. The predatory sophistication had advanced enormously. Where Dimetrodon relied on metabolic advantage and brute force, Gorgonopsians showed evidence of deliberate strategic hunting behavior. Brain endocasts suggest a level of behavioral intelligence well beyond simple opportunistic scavenging. Specialized foot anatomy allowed remarkably silent movement. Padded soles dampen sound during stalking approaches. Legs positioned more directly beneath the body than earlier sprawling forms enabled them to outrun any contemporary prey. Eyes positioned for forward-facing binocular vision combined with an advanced olfactory system for tracking prey over distance. Their hunting strategy was calculated. Deliver a devastating bite, retreat, wait for the prey to weaken from blood loss. Approach again. Ambush tactics included lunging from behind trees or rock formations with jaws wide open, the maximum gape angle accommodating the long sabers. Robust chest and powerful forelimbs were optimized for grappling with and pinning large prey. The saber-tooth morphology is a landmark case of convergent evolution. Nature independently produced saber teeth in at least 5 different lineages across 300 million years. Gorgonopsians were the first major example, predating Smilodon by 230 million years. Richard Lydekker first described them in 1890. Major Russian specimens were found by Anomalocaris in the early 1900s. Christian Kammerer's 2016 phylogenetic work refined our understanding of the group's diversity. The mainstream theory classifies them as ambush and stab predators, inflicting deep, bleeding wounds on megaherbivores. An alternative biomechanical analysis suggests the sabers were too fragile for bone contact and were used exclusively on soft tissue, a precision weapon rather than a bludgeon. The fringe proposal is metabolic. Their advanced adaptations have led some to argue Gorgonopsians were warm-blooded or near endothermic, radically ahead of their time. They were completely wiped out during the Permian-Triassic extinction. But to understand what they were hunting and what that prey's extreme defenses reveal about how dangerous this world truly was, we need to look at their primary target. Number 10. Scutosaurus. Scutosaurus karpinski lived during the late Permian, approximately 252 to 250 million years ago. It was a Prionosuchus from what is now Russia. It stood about 1.5 meters tall, 5 feet, and reached lengths of up to 3 meters, 10 feet. Weight estimates approach 1,000 kilograms, over 2,200 pounds. What makes Scutosaurus significant is not what it did to other animals, but what other animals did to it, and what its body evolved to withstand. It was covered in osteoderms, bony plates embedded directly in the skin, creating a biological shield over its back and flanks. These bony nodules formed within the dermis, creating a distributed armor layer that absorbs and deflects bite force across a wide area. Its thick, bumpy skull bore horn-like protrusions, likely used for headbutting contests within its own species or as passive defense against predators like Gorgonopsians. A large ear bone, the stapes, suggests a keen sense of hearing, specifically adapted to detect the approach of predators. Priosaurs were among the most successful large herbivores of the late Permian. They filled the ecological role that ceratopsians and ankylosaurs would later occupy in the Mesozoic. Scutosaurus had legs positioned directly under its body, a semi-erect posture necessary to support its massive weight. Leaf-shaped teeth were designed for grinding and shredding tough desert plants. Its digestive system likely included a huge gut chamber for fermenting fibrous plant material, similar to modern hindgut fermenters. It consumed massive quantities of low-lying, tough vegetation to fuel its enormous body. It believed to have moved in large herds for collective predator defense. Rather than fleeing, it relied on armor, bulk, and herd formation to discourage attackers. Essentially immovable, extremely slow, and ponderous. A walking fortress with no capacity for rapid escape, it likely produced loud, trumpeting, or grunting vocalizations to communicate alarm within the herd. Anomalocaris discovered major specimens along the northern Dvina River in Russia in the early 1900s. Michael Lee revised Priosaur phylogenetics in 1997. The mainstream theory holds that Scutosaurus was the primary prey base for the largest Permian predators, its defenses evolving in direct arms race response to Gorgonopsian predation. An alternative theory argues the osteoderms served thermoregulatory functions, mineral storage, and heat dissipation as much as defensive ones. Scutosaurus was obliterated during the Permian-Triassic extinction, the event that ended the entire Paleozoic era. And that extinction event deserves its own examination. The Permian-Triassic extinction event struck approximately 252 million years ago. It killed an estimated 96% of all marine species, and 70% of terrestrial vertebrate species. It is known as the Great Dying, the single most devastating biological catastrophe in the 4.5 billion year history of Earth. Every Permian creature we have discussed, Gorgonopsians, Scutosaurus, Dimetrodon's descendants, Prionosuchus, was erased. The extinction marks the boundary between the Paleozoic, meaning ancient life, and the Mesozoic, meaning middle life, a complete reset of global ecosystems. Recovery took approximately 10 million years, longer than any other mass extinction recovery in the fossil record. The kill mechanisms were cascading and overlapping: ocean anoxia, the depletion of dissolved oxygen, hypercapnia, carbon dioxide poisoning, acid rain. Global temperatures increased by 8 to 10 degrees Celsius. The Siberian Traps, one of the largest volcanic events in Earth's history, erupted approximately 252 million years ago. The eruptions released massive quantities of carbon dioxide, sulfur dioxide, and methane. Ocean acidification dissolved calcium carbonate shells, devastating marine invertebrates and reef ecosystems. Terrestrial ecosystems suffered what geologists call a coal gap. No coal deposits formed for 10 million years after the event, indicating total collapse of forest ecosystems. Plants were replaced temporarily by fungal blooms, the fungal spike visible in the fossil record. Douglas Irwin's seminal work Extinction, published in 2006, remains a foundational text. Burgess, Muirhead, and Boehrich's 2014 high-precision dating narrowed the main pulse to approximately 60,000 years. The mainstream theory holds that Siberian Traps volcanism triggered cascading climate collapse, volcanic winter followed by runaway greenhouse warming. An alternative geological theory proposes the extinction was multi-causal. Siberian Traps combined with contemporaneous methane clathrate release from ocean sediments, creating a double carbon injection. The fringe speculation proposes an extraterrestrial impact analogous to the asteroid that killed the dinosaurs. Disputed evidence from Antarctica, including the Bidyut structure and the Wilkes land crater, has been cited, but remains highly controversial. Coral reefs essentially vanished. Terrestrial plants suffered near total deforestation. Survivors were often small, generalist species, the ecological meek inheriting a devastated Earth. The extinction created the ecological vacuum that allowed archosaurs, the ancestors of dinosaurs, to rise to dominance. Small therapsids called cynodonts survived. They were the eventual ancestors of all mammals, including humans. The Permian-Triassic extinction is frequently cited as an analog for modern climate change. Paleontologists have noted that current carbon dioxide emission rates approach those estimated for the Siberian Traps eruptions, though over different timescales. The Great Dying demonstrates that planetary life is resilient but not invulnerable. Recovery happens, but on geological timescales incompatible with human civilization, and among the wreckage, a few organisms manage to persist. Helicoprion is notable as one of the few Paleozoic shark relatives to cross the Permian-Triassic boundary alive. It survived the event that killed 96% of marine species. But its survival was brief. The lineage went extinct in the early Triassic, unable to compete in the radically restructured post-extinction marine ecosystem. Post-extinction oceans were depauperate, meaning species poor, for millions of years. A dead zone of early Triassic marine life. Cartilaginous fish as a group showed higher survival rates than bony fish, possibly due to lower metabolic oxygen demands. Helicoprion's pelagic open ocean lifestyle may have buffered it from the worst coastal anoxia events, devastating shallow marine ecosystems. Its specialization on soft-bodied cephalopods may have been both an advantage, since that prey persisted, and a vulnerability, since it meant a narrow dietary niche. Work by Braillard and colleagues in 2009 documented the early Triassic marine recovery. Tapanila's 2013 research traced Helicoprion's post-extinction fossil record. The mainstream theory holds that Helicoprion survived due to its pelagic habitat and generalist chondrichthyan physiology, but could not adapt to the new Triassic ecological order. An alternative theory invokes dead-clade walking syndrome, where organisms survive the extinction event itself but are doomed by its aftermath, trapped in ecosystems too unstable and too different to sustain them. The fringe proposal suggests post-extinction marine chemistry was so radically altered, sulfidic and low oxygen, that Paleozoic body plans were fundamentally incompatible with the new ocean. Other Paleozoic survivors crossed the boundary. Coelacanths. Nautiloids. Certain brachiopod lineages, Some persist today as living fossils. The concept of evolutionary bottlenecks applies here. Mass extinctions do not select for the best organisms. They select for the luckiest and most generalized. Post-extinction ecosystems were dominated by disaster taxa. Opportunistic species like the bivalve Chlorea that thrived in disrupted environments. The Triassic recovery saw entirely new marine predator guilds rise, ichthyosaurs, nothosaurs, and early marine reptiles replacing Paleozoic fish. Anomalocaris, Arthropleura, Jaekelopterus, Dunkleosteus, all of these were long gone before the Great Dying, victims of earlier, smaller extinctions. The Paleozoic's lesson is clear. Specialization is a double-edged sword. Armor, saws, and saber teeth dominate until the environment shifts. Understanding extinction survival traits now informs conservation biology, helping predict which species traits confer resilience to rapid environmental change. And the handful of survivors that crossed the Permian-Triassic boundary carried the genetic legacy of 300 million years of Paleozoic evolution into the Mesozoic, a thread of continuity through catastrophe. But every creature in this documentary was completely unknown to science until the 19th and 20th centuries. Their existence was buried under hundreds of millions of years of geological overwriting. How were they lost? And how were they found again? Pre-scientific cultures interpreted fossils in the only frameworks they had. Chinese dragon bones, which included Paleozoic marine fossils, were ground into medicinal powder. European traditions saw giant bones as the remains of biblical figures or mythological beasts. The founding of modern paleontology traces to Georges Cuvier's 1796 demonstration that extinction was real, a radical idea that contradicted the prevailing belief in a perfect, unchanging creation. The challenge of reconstructing these animals is immense. Soft tissues, cartilage, and small organisms rarely preserve. The Paleozoic fossil record is heavily skewed toward hard-shelled, bony, or mineralized organisms. Anomalocaris exemplifies the problem. Its arms, mouth, and body were classified as three separate animals for nearly a century before Whittington unified them in the 1970s. Helicoprion's tooth whorl was misplaced on virtually every part of its body for 114 years from 1899 to 2013, before CT scanning resolved the debate. Dunkleosteus was first described from fragmentary armor plates. Complete reconstructions required decades of comparative anatomy. The Burgess Shale, discovered in 1909 in British Columbia, and the Qingjing Biota, discovered in 1984 in Yunnan, China, revolutionized understanding of Cambrian life. Key figures include Walcott, who discovered the Burgess Shale, and Whittington and Derek Briggs, who reinterpreted the Cambrian fossil record in the 1970s and 80s. Neil Shubin's work has connected Paleozoic anatomy to modern body plans. The mainstream approach uses cladistic analysis and comparative anatomy to reconstruct extinct organisms from fragmentary remains. Alternative methods now include CT scanning, synchrotron imaging, and computational fluid dynamics, allowing biomechanical analysis of fossils without destructive sampling. The fringe controversy is what some call paleontological imagination, the argument that reconstructions of animals like Anomalocaris involve excessive speculation from minimal fossil evidence. Ghost lineages present another challenge, periods where a lineage must have existed based on phylogenetics but left no fossil trace. Molecular clock analyses sometimes contradict fossil evidence on when lineages diverged, creating ongoing tension between genetic and morphological dating. Plate tectonics, erosion, metamorphism, and subduction have destroyed the vast majority of Paleozoic fossil-bearing rock. Only a tiny fraction of Paleozoic species are known to science, estimated at less than 1% of total biodiversity. Paleontological illustration has evolved from crude Victorian sketches to photorealistic digital reconstructions, informed by biomechanics, pigment analysis, and phylogenetic bracketing. 3D printing of fossil reconstructions and virtual reality Paleozoic environments are making these creatures accessible to public education for the first time. The rediscovery of these animals represents one of science's greatest detective stories, reconstructing lost worlds from fragments of bone, shell, and stone. And these lost worlds are not just curiosities, they are blueprints. Dunkleosteus' self-sharpening jaw plates directly parallel the design of modern self-sharpening industrial cutting blades. engineers independently reinvented a principle that natural selection discovered 360 million years ago. Anomalocaris' 16,000 lens compound eyes have inspired research into wide-field optical sensors and multi-aperture camera systems for robotics and surveillance. Arthropleura's segmented flexible armor informs modern research into articulated protective gear for military and industrial applications. Meganeura's flight mechanics influence microdrone aerodynamic design. Scutosaurus' distributed osteoderm armor is studied as a model for composite impact-resistant materials, spreading force across embedded rigid elements within a flexible matrix. This is what researchers call convergent engineering. Natural selection and human engineering often converge on identical solutions, streamlining, armor layering, shearing mechanisms, because physics constrains both. George Loader at Harvard studies fish biomechanics. Robert Full at USC Berkeley investigates arthropod locomotion. Various DARPA-funded programs explore biomimetics drawn directly from the fossil record. Jaekelopterus' Chelicera biomechanics have been analyzed for robotic gripper design, particularly underwater manipulation systems. Helicoprion's continuous tooth whorl growth system is studied in dental research for understanding continuous tooth replacement. Computational fluid dynamics applied to Paleozoic body plans reveals hydrodynamic principles useful for submarine and underwater vehicle design. Paleozoic extinction patterns inform modern conservation triage, identifying which trait combinations predict vulnerability to rapid environmental change. Some astrobiologists use Paleozoic organisms as models for predicting what alien life might look like under different atmospheric conditions: high oxygen, high carbon dioxide. Prionosuchus' ambush predation strategy is studied in behavioral ecology as a baseline for understanding how apex freshwater predation shapes entire river ecosystems. Dimetrodon's sale has directly influenced passive solar heating research. The Permian-Triassic extinction's carbon dioxide-driven ocean acidification is used as a direct geological analog for modeling current ocean acidification trajectories. Gorgonopsian saber-toothed convergent evolution demonstrates nature's preferred solutions to large prey predation. Modern coral reef conservation draws on Paleozoic reef collapse data to predict threshold tipping points for modern reef systems. Paleozoic atmospheric models directly calibrate climate models used for a future climate projection. Every engineering challenge humans face, cutting, armoring, sensing, thermoregulating, moving efficiently through fluid, was solved by Paleozoic life first, using nothing but the fundamental laws of physics and chemistry. The Paleozoic era spanned roughly 290 million years from the Cambrian explosion around 538 million years ago to the Permian-Triassic extinction approximately 252 million years ago. Every major predatory strategy used today, ambush, pursuit, armor piercing, venom, pack hunting, was pioneered during this era. These organisms engineered solutions to survival using only the fundamental laws of nature, physics, chemistry, and thermodynamics. The armor of Dunkleosteus, the optics of Anomalocaris, the thermoregulation of Dimetrodon, all are expressions of universal physical principles. Mass extinction erased them, but the principles they embodied are eternal. The fossil record preserves less than 1% of Paleozoic biodiversity. What we have covered is a fraction of a fraction. Modern technology, CT scanning, computational modeling, synchrotron imaging, continues to reveal new details from old fossils. The Permian-Triassic extinction's parallels to modern climate change are not metaphorical. They are geochemically measurable. Every creature in this documentary was real, not a myth, not a monster. A product of natural selection operating on deep time. 10 organisms across approximately 300 million years, from Cambrian oceans to Permian deserts. These animals did not just survive. They dominated for hundreds of millions of years, using designs we are only now learning to replicate. Innovation using fundamental laws of nature is not a human invention. It is the oldest story on Earth.